In this video, let us now discuss how to apply the branch and bound technique to solve the knapsack problem. So here we would be discussing 0-1 knapsack, which says that you either include the item into the knapsack entirely or discard it entirely. That is, you are not going to consider the fractional parts of the knapsack. So this problem says that you are given n items of known weights Wi and values Vi ranging from 1 to n and a knapsack with a capacity of W. Thus, we are here supposed to find the most valuable subset of items that fit into the knapsack. Therefore, the motto here is to maximize. The motto here is to maximize the profit. That is being earned. So therefore, we say that the sum of the profits of including all the elements that fit into the knapsack should be maximum. Similarly, the weight of all the elements that you are going to include into the knapsack, the sum of weights of all the elements that you are going to include into the knapsack should always be less than or equal to the weight of the knapsack. Therefore, it is convenient to order the items of a given instance in descending order by their value to weight ratios. Then the first item will always give the maximum profit. The first item gives the best payoff per weight unit, and the last one gives the lesser profit or per weight unit, with ties resolved arbitrarily. Each node on the ith level of the tree, the state space tree, where I ranges from 0 to n, represents all the subsets of n items that include a particular selection made from first I ordered items. This particular selection is uniquely determined by the path from root to the node. A branch going to the left in the state space tree always indicates the inclusion of the next item, while a branch going to the right indicates that it is an exclusion. Please remember this. A branch going towards the left represents inclusion, and a branch going to the right indicates the exclusion of the element. And then we record the total weight W and the total value V of this selection in the node, along with the upper bound that is being calculated on the value of any subset that can be obtained. That can be obtained by adding some 0 or more items to this selection. The simplest way to calculate the upper bound is given by UB. Upper bound is given by UB is to add to V the total value of the items that is already selected. The product of remaining capacity, that is, for calculating UB, you will add V, that is the total value of items already selected, to the product of remaining capacity of the knapsack, which is given as capital W minus small w, which is multiplied by the best payoff among the remaining items given as V I plus 1 divided by W of I plus 1. So here the capital W stands for the entire capacity of the knapsack. So when you add an item into the knapsack, then the small w represents the weight of the item that you are adding. So if you remove the weight of the item that is being added to the weight of the knapsack, then you get the value that is the remaining capacity of the knapsack. So now let us consider a specific example. Try to apply branch and bound algorithm to this example to find out the maximum profit that we can achieve with the value of the knapsack or the knapsack capacity that is equal to 10. Right, so the problem says that you have 4 items 1 2 3 4, and the weights of these items are 4753 respectively, and the cost or the profit of these items are $40 42 25 12 respectively, and the value bar weight ratio here is 10 6 5 and 4 respectively. So we assume that we are going to arrange these values in the ascending order of their value weight ratio. So at the root of the state space tree, that is at the root of the state space tree, no items have been selected as yet, and hence both the total weight of the items already selected, that is W, and their total value are equal to 0. Right? So total weight and total value is equal to 0. And the value of the upper bound computed by the previous formula, that is UB equal to V plus W minus W Vi plus 1 divided by Wi plus 1. So the value of not including any element is 0, plus the weight of the knapsack, the capital W here is 10, minus small w, we are not including anything, so it is again 0. So 10 minus 0 is 10 itself, and the payoff weights of the remaining elements, that is the payoff weight of the first element here is 10. So it is a product of 10 into 10. So therefore upper bound is equal to 100. So you can see in the node the initial upper bound is set as 100. So now we shall try to consider the selection of the first item into the knapsack. So again here in the first iteration for the first item we'll have to compute two possibilities. That is, the first possibility is what would be the upper bound if we try to include an element, And what would be the upper bound if we do not include the first item, right? And always here we are trying to we are trying to obtain a maximum upper bound because it's an maximization problem. That is, we want to earn maximum profit out of these objects. So here, let us now first consider item 1, try to include it in the knapsack and calculate what would be its upper bound. So upper bound is equal to, when you are trying to include the first item, so the value of the first item is $40. So it is 40 plus the capacity of the knapsack is 10. So 10 minus the weight of the first object is 4 into the payoff of the next object is 6. Right? So 40 plus 36, this is 6. So 40 plus 36 is equal to 76. So similarly, if you try to calculate the upper bound for not including item 1 into the knapsack, then it will be equal to the value of the first item is again 40 plus the weight of the knapsack here is 10. Sorry, you are not including the first item into the knapsack, so upper bound is equal to, when you are not including it, then its value tends to be 0 plus, and then the weight of the knapsack here is 10, so 10 minus, you are not including the item into the knapsack, so its weight also becomes 0 into the payoff of the next element is 6. So therefore it becomes 10 into 6, that is equal to 60. So the upper bound of not including the item into knapsack is equal to 60, and the upper bound of including the item 1 into knapsack is 76. So we go for the maximum profit. So therefore we consider the first scenario. So let us now draw the state space tree of it. So here you can see the left side branch says that it's inclusion of the first item. So the weight here is 4, the value is 40, and the upper bound is 76. And without including 1, the upper bound is 60. It is lesser than 76. So therefore it is an inferior, or it's a non-promising node. So therefore we leave it off. So for the next time, we now try to compute whether to include item 2 into the knapsack or not. So again, apply the same formula to calculate the upper bound here. So what do you get? So if you are trying to include item 2 into the knapsack, then the weight of the second item is 7. Weight of the second item is 7. The value of the second item is 42. Right? So here, including an item into the knapsack, item 2 into the knapsack, here becomes 11. So you got to apply the same formula here. So it becomes equal to 11, whereas the value of the knapsack for not including item 2 becomes equal to, so if you apply the formula, it will become 0 plus 4 plus 4. So our upper bound here becomes equal to the upper bound here becomes equal to 40 plus 6 into 5, that is equal to 70. So let us try to include the second item into the knapsack. So while we try to include the second knapsack into the second item into the knapsack, then the remaining capacity of the knapsack is now equal to 6. Right, because the first item's weight is equal to 4. So once you included this item 1 into the knapsack, the remaining capacity of the knapsack has become equal to 6. And as it is a 0 1 knapsack, you can possibly include the entire item into the knapsack, or you'll have to discard the item. So if I think of including the second item into the knapsack, then the weight of the item is 7, which is greater than the capacity of the knapsack, right? So therefore weight becomes equal to 11 if I try to include the second item into the knapsack. 6 plus 7 equal to 11, so therefore it's not feasible. We eliminate or we terminate this node. And then coming on to, without including item 2, what would be the upper bound? So here the weight of the first item was 4, so left out capacity of the knapsack here would be 6. So our formula V plus W minus W into Vi plus 1 divided by Wi plus 1 now becomes equal to V. When you are not including an item itself, then you are not going to achieve any more profit. So you will be surviving with the previous profit, that is 40 plus the remaining capacity of the knapsack given by W minus W, which is equal to 6, because already I have an item 1 with capacity or with a weight of 4 in it, plus the payoff of the next item is 5, right? This is the product. So therefore it now becomes equal to 70. So the upper bound of not including second element is equal to 70. Okay, so this is how our state space tree looks like after the second iteration. So now, and node 4 now tends to be the most promising node. So now let us move on to the next phase, that is, let us try to include the third item into the knapsack, and let us also examine a possibility of not including the third item into the knapsack. So let us move with the first possibility, that is including item 3 into the knapsack. So first calculate the weight. So what is the weight of the third item? So the weight of the third item is 5, and the previous weight of which is already existing in the knapsack is equal to 4. So 4 plus 5 is equal to 9, which is within the capacity of the knapsack. So therefore let us now calculate its upper bound. So upper bound is value plus the remaining weight into the payoff, right? So what is the value now? So from the previous step we have the value as 40, plus including the third element will give us 25 more dollars. So 40 plus 25 is 65. So this 65 plus the remaining weight of the remaining capacity of the knapsack. So 4 plus 5 is equal to 9. So your knapsack is left out with only one one empty space, into the payoff of the next element is equal to 4, right? So it is now 65 plus 4. 1 into 4 is 4. So the upper bound is now equal to 69. Right? Similarly, let us now calculate the upper bound for not including item 3 into the knapsack. So when you do not include item 3 into the knapsack, then the weight remains equal to 4 itself from the previous step, and the value also remains 40 itself from the previous step. So then what is the upper bound? So upper bound becomes 40, that is value from the previous step, plus the remaining capacity of the knapsack is, when 4 is consumed, you are left out with 6 more spaces. So 6 into the payoff of the next element is 4. So it is 40 plus 6 into 4, that is equal to 64. So the upper bound now becomes equal to 64. So again, it's a maximization problem. So we go with the maximum profit, that is 69. And the other one, we consider it to be the inferior amount, so we will discard it. So then the last possibility, we shall also check the last possibility, that is to include item 4 or not into the knapsack. So here we have included item 3 into the knapsack. So the total weight here is 9, and your left out capacity of knapsack is exactly 1 unit, right? And the weight of the incoming item is 3, which is greater than 1, right? So therefore the weight would now become 9 plus 3, that is equal to 12, which is greater than the capacity of our knapsack, so it is not feasible, we discard it. So we then go for without including possibility of checking without including item 4 into the knapsack, what could possibly be our upper bound. So therefore, when you are not including the item itself, then the weight remains as it is. Weight is equal to 9, and the profit also remains as it is, that is equal to 65. So now apply the formula. So it now becomes value. So value is 65 plus the left out capacity of the knapsack is 1 into the payoff of the next element. We don't have the next element here, so weight into weight bar value ratio of the next element, we consider it as 0. So now the upper bound equation becomes equal to 65 plus 1 into 0. So therefore upper bound tends to be equal to 65, right? So therefore the optimal solution or the final solution vector now has items 1 in it, right? And followed by it, our optimal solution vector has item 1 in it, and then we traverse the side, but we have not included item 2 in it, and then we have item 3 included in it. Again we traverse the side, the state space tree, but we have not included item 4 in it. So therefore our optimal solution has only items 1 and 3 included into the knapsack, with an optimal solution, that is the value to be maximum value, which is equal to 65.